Yeah, we do lots of cool stuff with Doubleword. Hopefully, I'm going to leave you today with some lessons about some of the stuff we've been building. They're a bit more open source. I'm going to talk about how I built it on top of our Doubleword server, but everything I talk about today can be ported to any inference server, any OpenAI compatible interface, and all the tools I'm using are free, available, and I'll link the repos at the end. So I want to talk today about the paradigm of parallel agents. By show of hands, how many people actively run parallel agents right now as part of their workflow, either personally for productivity or as part of a company? Seb, you don't count. You work with me. Okay, awesome. Well, a few people, so that's good, but not as many as it should be. So today I want to talk through how you can take advantage of a paradigm called the swarm, and I'll touch on why it's got that name and why it's useful for certain tasks. Not that synchronous agents aren't, but they're useful tools for different objectives. So this is what I want you to take away from today. We're going to start with differentiating when you should use parallel agents, and this is predominantly for wide, parallelizable or shareable work, which in the context of comparing against a synchronous agent, parallel agents perform far better. And I'll touch on the details of that, and then I'll bring it down to a bit more of the details about how you actually build these models. And the takeaway is that you let the model decide the team and decide the parallelism, and you just have to build a small amount of scaffolding, which gives you your runtime to facilitate this. So let's start about why swarms. I think a useful place to start here is to look at a paradigm and call out a reflex that I know I myself am guilty of, which is to reach for these frontier models which have massive context windows and are incredibly smart to achieve any task that I need doing. Now this can be really tempting and is a great tool. It's what I would call a hammer, and hammers are a fine tool, but if you give a man a hammer, all he sees is nails, and I have been that man hammering everything under the sun. And actually, I want to prove to you that for some contexts, for some use cases, it's actually a worse tool. And to do that, I'm going to use an experiment. So we're going to be auditing an open source repo. For this, the demo, I'm going to be using our control layer, which is our AI API gateway. It's roughly 512 source files, which is around 2.5 million tokens of unique context for an agent to pass. And what we're going to be doing is trying to find security vulnerabilities in the repository. So the takeaway we want from this is to be able to give a brief report to our development teams to improve and fix bugs before they cause outages in production. So we're going to run it with a solo agent, and then we're going to run it in a swarm paradigm. So first, let's look at how the hammer does. So as I mentioned, 2.5 million tokens, that's sort of the floor we're optimizing against. Obviously, we're never going to get down to only being as efficient as using 2.5 million tokens, because you have to view everything at least once, and you're going to have some generative tokens on top of that, as well as some extra input tokens. But I fixed Claude Opus 4.8 to not be able to run any parallel tools, to stay in a single agent, single context, and just pass the entire repository and figure out where all the security vulnerabilities in the repository was. Now, this is obviously hamstringing it, but for the purposes of explaining why this paradigm of parallel agents are useful, we can see that it managed to chomp through, on my projections, would have chomped through 300 million tokens, which would have cost me $300, and roughly that is with prompt caching and effectively perfecting the cache control you can set with Anthropic. If you didn't do this effectively, you could spiral up to a 2K bill for passing this repo. I got to about 7% coverage of the repo before I lost patience and burned 30 million tokens. And 95% of these were repeated cache reads. So this is the agent just feeding back into itself things it's already seen, and its chat context just growing exponentially until it hits its 1 million barrier, and then it's constantly having to compact, put new information in, maybe lose old information that was valuable. And so I don't have tangible performance benchmarks of how it did on finding the security vulnerabilities because I didn't run it to the end, but you would have to imagine that it's losing context throughout only being able to view just under half of the code base at any given time, excluding all the extra chat and generation it's created. So the alternative, what I want to talk to you about today is going from this paradigm of one expert in sequence to a team in parallel. And we've already solved this as humans. We've built companies which operate in this paradigm. You have operatives, which are human beings, who have short, bounded context and specific skills to achieve tasks. The CEO of the company does not sit there and execute all the most important tasks, but we pay them the most amount of money, and in theory, they are the smartest people. Not always, I don't know. You have highly effective individuals with smaller context who don't see the whole picture, but are better at executing the individual tasks and report just the findings back to the higher managers. So how do we actually build this? So I'm going to ground this to the use case of a security review, but then I will show you at the end how this parallelizes to any use case you can think of. So this is all inspired, and the name Agent Swarm comes from a paper published by the Kimi team from Moonshot AI. They published their new training methodology for their Kimi 2.5 model in February of this year. And this essentially introduced a new algorithm for the training called PARL. This is Parallel Agent Recursive Learning. And essentially what they designed here is they would have a training mechanism where they have the Kimi model running with this orchestrator spinning off as many sub-agents as it would need to achieve a task. And they have the recursive algorithm, which was learning, and it would only train the orchestrator, would take into account how much parallelism the model chose to achieve the task, and would factor that in on how well it achieved it at the end and fed it back into the learning. So the Kimi model was learning how to be a good CEO, how to split a large objective into smaller tasks, start those tasks, and audit the findings. So this is the framework that I've tried to replicate, and I want to explain to you in a bit more detail. But they found like really good results. I can link the paper, and it's down here, and you can find it later and read it at your own leisure. But they found almost a 5 times speed up on like end-to-end latency of these longer tasks. They were particularly interested in deep research, and on the browse comp benchmark, they went up 18 points pretty much just from using this paradigm. So what's remaining for us to build? So Kimi 2, they have 2.6 out now, but it's trained with the same algorithm, is open source. There's open weight models, and there's APIs that we can use. Moonshot themselves have an API where they offer this agent swarm already built that you can take advantage of. But what if you wanted to get into a bit more of the nuts and bolts and build it for yourself? What if you wanted to port it to any open source model that you have running? What if you don't want to pay the overhead of using their API? So I'm going to step through how you can build the scaffolding that they're offering behind the API. And this can feasibly be used in any tool calling LLM. It happens that I've used the Kimi model because, as I mentioned, they trained it to be able to achieve this task. So you would think it was beneficial, but any good open source model would be able to achieve this task as well. So the agent swarm relies on 4 principles. As I mentioned, there is a self-designing orchestrator who is your CEO. He is the person, or she is the person, not very inclusive, who decides the team and the composition to achieve the task you give it. So you give it a higher overarching task to achieve, and then you leave it to the agent to create personas and execute and give those personas tasks. The big one and the big saving is the bounded local context. So in the solo agent I showed you before, how we exponentially grew to 300 million tokens consumed was because the same agent had to manage the entire context of the task and the entire repo, which was huge. And that fed into itself to create this massive spiral of context. The bounded local context means that the orchestrator never sees what the workers that it starts actually do. It only ever returns back structured findings. And so you never have to repeat the context of the findings of the workers from their individual tasks in the orchestrator's loop. And then you never have to, the individual workers don't have to worry about the entire context of the repo because it's only given a small bounded task, which is far more efficient and saves this repeated token usage. And we included a little addition to the algorithm, which was including this like structural anti-think, which we had an independent agent, which then checked the findings of the agents at the end, basically to make sure the agent wasn't hallucinating, because giving developers times and making them chase down vulnerabilities that don't exist is extremely frustrating. So we wanted to add this extra sort of process in the swarm. And then finally, you have a final pass, which is the synthesis, which is where you take all the structured findings, which are quite concise, without any of the context of how it got them, and then you synthesize them into a report. And for the audit, we would classify these by vulnerability level, whatever you call it, critical. Cool. So the architecture, as I mentioned, the CEO sits at the start. It's given, in the audit case, a repo and a map of the file structure. It's then responsible for creating the personas that it needs to execute and the tasks. It then starts these parallel agents, which can spawn up to hundreds. And it does them in waves. So it will start them all off at the same time. They'll all go away, and then they will report their findings to the verifiers, which will either refute or let them survive. And then finally, they're taken through this final pass of being composed into this final report. So the orchestrator, as I mentioned, we've sort of gotten this in. This is the nuts and bolts of how it works. It has two functions. It creates sub-agents, which I call like personas. So you create a name, which is sort of like a foreign key. No, primary key. And then a system prompt. So it's a spiel of what it does. Like, for instance, during a natural run, we had this was trying to find security vulnerabilities, so it created a persona which was an injection file system, so you hunt injection and unsafe file access throughout the repo. And then each time that agent is given a task, it is invoked with the same system prompt and given a very tight spec of files to look at, tasks to achieve, like maybe like a certain number of files to scan, etc., etc. But then every agent is starting with its own persona, and every sub-agent is starting with its own persona. And then workers only see their slice. I mentioned this in the sort of context sharding. You don't see the whole context the orchestrator has, and you only see your small part of your task. So it may be like two files. It may be loads of files, but only like certain parts of it that you'd have to grep. And the workers have their own tools, which are defined in the schema. So for this sort of V1, we only implemented read tools. The Kimi paper implements all sort of tools. It has like terminal execution, actual editing of files to do different use cases. For a security audit, you don't need to edit the code. You just need to figure out the vulnerabilities and report them. So this was a good first step. And then they use constraint generation to produce their report at the end of it, which is concise, token light, and doesn't incur extra costs, or at least I claim. And then every finding meets its skeptic. So this is just an independent verifier that just sits and waits for the reports from each worker, and in isolation of the finding, double checks. This is just to stop workers as they sort of go on their cycles of looking. They can sort of convince themselves of problems that aren't there. So this is like a fresh context. Let me look at this from fresh again. Is this actually a genuine problem? If it is, it survives. If it's not, it gets removed. And then one pass to write the report, as I said, classifying them as high, medium, or low vulnerabilities. So this was all talking through how the swarm works specifically for security audits. This can also be generalized to other use cases. All that you need to change are the prompts that you use. So this will be the prompt to the orchestrator, essentially like the overarching task you want to achieve. The prompts to like your verifier if you're running it, and then finally your classifier at the end, which is collating all the findings. Like maybe for an onboarding doc, you don't need to classify the findings. You need to structure it in a sensible, cohesive story for a developer to understand how to run the repo. You need a schema which is the shape of the findings. So for a security audit, it could be like level, I don't know, reference to the file that it's in. For an onboarding doc, it might be something different. And you can see for research, it might be a URL link to the source that it's found the information from. And then you define the tools that the workers can use. So whether they can execute terminal commands, whether they can actually edit files. For us, we just affixed it to read. But if you were doing wider research, you'd give it a web search tool, et cetera, et cetera. And actually, the wide research is what the Kimi team based the most of their training data on. So what was the results? So the same audit, fewer tokens is kind of the vibe. We managed to get it down to 5.6 million tokens. Obviously, this is still healthily above the 2.4, was it, million tokens in the repo. So you can't reduce it all the way to the limit, as you'd hope, but you can 53 times reduce the amount of tokens you need to process. Obviously, the cost is a little bit skewed because we're using a cheaper model of the Kimi 2.6 on the Doubleword inference server. But regardless of that, it's still a significant performance improvement, efficiency improvement, and tangible results and actual vulnerabilities were found and need to be remediated from this report. So it's incredibly more efficient, better performing, and costs you less. So yeah, I think it's a very useful paradigm. But could we go further? So if you think about the use case I've spoken about today of the security audit and this idea of parallel agents, we can actually step a bit further, because what we've used is a real-time API. And a real-time API, we're paying for a performance that we don't necessarily need. We're paying for like low latency on time to first token, and we don't necessarily need that in every case. We care more about the global throughput of tokens we're getting necessarily than the individual latency of any single request. So, helpfully, and a bit of shameless self-promotion, on the Doubleword server, we have a paradigm that we call asynchronous processing, where you pay less for your tokens and you forfeit a little bit of latency for still a high global throughput of tokens. So by using the service tier flex on either the chat completions or responses, OpenAI compatible API, you then get a 30% reduction on any of your inference requests and your tokens, both input and output, because your individual requests may wait a little longer, like one request might take a little bit more time to get its first token. But when you do get your tokens, they still move globally at a higher throughput and the same as if you would get from using a low latency API. So we think for these asynchronous paradigms of processing, this is a far superior method of submission. Also, helpfully, with the responses API, you can use a background method of submitting your request and polling for the results, rather than trying to keep hundreds of HTTP connections open at once, which is a very inefficient way and is bound to lead to drops and retry mechanisms. So that's pretty much all I wanted to cover. If you want to go and run this, this repo is open source. It's hosted on the Doubleword repository. You can go write your own briefs, invent your own tasks for that you want to run. You can run it with the Doubleword CLI, which will auth you to our inference API. And also, we're running a promotion at the moment where we'll match your first deposit up to $50 of free credits. And I know how much all your inference bills are, so I'm sure you need to take advantage of this offer. But yeah, thank you very much. If anyone has any questions, very happy to dive in, but thank you for listening.
Two questions I have. One is that you did a comparison between the token-based bills and so on, but what about the overall compute cost used for spinning up sub-agents versus running a single one? That's one question. And the other question I had is, what's the, protocol or mechanism the orchestrator communicates with the, basically with the sub-agents? There's just, how the sub-agent received the task and send back the results and so on. What's that mechanism of communication channel, if there is any between them, or it's just prompts?
So it's just prompts. So the findings are reported back in like temp file system. So they write to file system and then it reads them. As your first question around the CPU, I don't actually know the amount of CPU used by the solo agent compared to the parallel agents. I imagine the parallel agents use more, obviously, because they spawn subthreads. But you would think because they complete faster, hopefully it equals out to using roughly the same.
So just to imagine, this is running inside of the same, let's say, VM, or this is somehow orchestrated like on top of like Kubernetes or something like that's was not entirely clear.
Yeah, this is all just running in, sorry, this is all gone off. But yeah, it's just running in a single like process on a single machine.
Okay, so
there's no sandboxing.
are like threads basically
yeah.
in this use case.
Yeah,
Okay.
exactly.
All right, thank you.